Hi everyone, today we'll discuss about all experiments in EDC lab, how to do all the experiments in EDC lab. First one is a PN junction diode. PN junction diode. This is the forward bias circuit. Forward bias circuit. Positive of the supply. This is RPS, 1 kilo ohm resistor, ammeter, voltmeter. 0 to 200 milliammeter, 0 to 20 voltmeter. Positive of the battery or positive of the supply is connecting to the positive of the diode. This may be silicon diode or germanium diode. Positive is connecting to positive, that is forward bias. So in between we are going to use one resistor safety purpose, and for the measurement of current we are using one ammeter. So positive is connecting to positive of the diode in between resistance and ammeter, and parallelly we are going to connect one voltmeter for the measurement of voltage. This is forward bias circuit. By varying RPS, 0, 0.1, 0.2, 0.3 and so on, we can find voltage and currents. That is forward bias of PN junction diode. It may be germanium or silicon. By keeping RPS 0 volts, what is the corresponding voltage and current? Note down that. Then next, keeping RPS 0.1, note down voltage and current. 0.2, 0.3 and so on. Repeat that for up to some values. Maybe up to 10 to 15 values you can take. Here you may get for germanium, after 0.3 you will get current constant, current increases, and for silicon you will get 0.7 cut-in voltage. That means the current increases at the 0.7 voltage. This is a forward bias circuit. Similarly, you can go for reverse bias circuit. You may change the diode direction. Similarly, you can change the voltmeter into microammeter, milliammeter into microammeter. That is the modification. One change is you can change the diode direction. Second one is in place of milliammeter you can take microammeter. Why? Because in PN junction reverse bias you will get very less current. That is why you can take microammeter. So that is about reverse bias circuit. And again same procedure, by varying RPS you can note down the corresponding voltage and current values. That means by keeping 0, what is the voltage and current? By keeping 0.5, what is the voltage and current? By keeping 1, what is the voltage and current, and so on. You can do that. The current increases slowly due to magnetic carriers. This is reverse bias characteristics. After that, you can find static and dynamic resistances. Static resistance is nothing but voltage by current. Single value you can take from the curve. It may be for silicon or germanium, both in forward bias and reverse bias. Similarly, you can find dynamic resistance delta V by delta I. That means V2 minus V1 by I2 minus I1. Any two corresponding voltages you can take on the curve and corresponding currents on the curve. It may be silicon or germanium. Their current is in, it may be in forward bias milliamperes. So into 10 power minus 3 you can take. It may be in reverse bias 10 power minus 6 for the current. So then you can calculate static and dynamic resistance. This is a PN junction diode, forward bias and reverse bias for both silicon and germanium. Similarly, you can go for GNR diode. This is GNR diode. GNR diode forward bias is same for the PN junction diode forward bias. So this is a positive is connecting with diode positive, same resistance, same ammeter, and corresponding voltage at the diode. So same, by connecting this, vary the RPS and note down the voltage and current values, 0, 0.1, 0.2, and so on. So PN junction diode forward bias characteristics and GNR diode forward bias characteristics both are same as you'll get. Maybe here we are using silicon, that is why 0.7 will get a cut-in voltage. Then come to reverse bias. In the PN junction reverse bias, we are getting breakdown voltage at the higher voltages. To avoid that problem, we are using GNR diode. That may be regulation characteristics or GNR diode characteristics. In the GNR diode characteristics, by varying this diode, you can replace or exchange this diode. That is the reverse bias. Just change this direction, positive to the ground and negative to the voltmeter or ammeter. Change the diode direction, that is becoming as the reverse bias. Then by varying the supply voltage 0, 0.1, 0.2, 0.3 and so on, otherwise 0, 0.5, 1, 1.5, 2, 2.5 like that. Then note down the corresponding voltage and current. That is the characteristics of the GNR diode reverse bias. By increasing the applied voltage, you may get constant voltage, but current increases. But voltage is constant. That we have to find here. Maybe for this diode, you may get 5.1 volts as the breakdown voltage, that is known as the Zener breakdown voltage, that we have to find. That is nothing but Zener did acts as the voltage regulator. That is the second experiment. Here you have to focus on this VZ. Then come to third one, rectifiers. It may be half wave, full wave. This is the half wave rectifier, this is the transformer, single diode, and output we are taking at the load resistance RL. Here we are using 1 kilo ohm resistor. This is without filter. Here we are going to operate without filter and with filter. This is the transformer primary and this is the transformer secondary. The transformer secondary is having 3 terminals, positive, ground and negative. So here in half wave rectifier, this is half wave rectifier. For this half wave rectifier, we have one transformer, one diode, and output is taken across the load resistance RL. The output may be at voltmeter or from CRO you can collect output. You may find voltage from voltmeter or you can find the output waveforms and voltage from the CRO also. Anyone you can do. Then the formulas are ripple factor is equal to VAC by VDC. After connecting this, here you may find in voltmeter VAC mode and DC mode. Keep voltmeter in AC mode, then find out VAC. Keep voltmeter in DC mode, find out VDC. VAC by VDC you will get. This is the ripple factor formula. Theoretically, the ripple factor formula is square root of Vrms by VDC whole square minus 1. Square root of Vrms by VDC whole square minus 1. Vrms value is Vm by 2. This is Vm by 2. And VDC is Vm by pi. VDC is Vm by pi. Substitute here Vm by pi and Vm by 2 whole square. Nothing but Vm square get cancelled. Pi square by 4 minus 1 square root of. That value is 1.21. So theoretically the ripple factor for half wave rectifier without filter is 1.21. So whenever you are calculating through voltmeter, then ripple factor is equal to VAC by VDC. That should be also approximately equal to 1.21. Ripple factor only we are calculating. Similarly with filter. If you connect one capacitor parallel to the resistor, C, that is capacitive filter. If you connect capacitive filter, that is nothing but half wave rectifier with filter. Here the formula is 1 by 2 root 3 into F into C into RL. 1 by 2 root 3 into F is 50 Hz given input frequency, and C is, here we are taking 100 microfarads, 100 into 10 power minus 6, and RL is 1 kilo ohm. If you substitute all the values, you will get 0.05. So for this also you can, this is theoretically 0.05. Similarly, you can take practical values from the voltmeter, same as VAC and VDC by connecting capacitive filter. VAC value will get, VDC value will get. You can find VAC by VDC, that should be equal to 0.05. That is both theoretically, practically we are finding the ripple factor values. Then similarly go for full wave rectifier. Here circuit is only different. This is the transformer. Here we are using 2 diodes and across RL we are taking output. It may be voltmeter or CRO. If you connect CRO, you will observe the waveform. If you connect voltmeter, you may get directly voltage. So here positive, negative and ground terminal. This ground terminal is connecting to the load resistance. These 2 diodes are connected together, and positive is connecting to diode 1, negative is connecting to diode 2, D2. So middle terminal is connecting to the load resistance. So the transformer secondary, positive, negative and ground. This ground terminal is connecting to the resistance. Across this you can find the output. Same procedure, VAC by VDC. You may get that value. Same, you can substitute Vrms by VDC whole square minus 1. Here VDC is 2 Vm by pi. Vrms is Vm by root 2. For full wave rectifier, VDC is 2 Vm by pi and Vrms is Vm by root 2. If you substitute all these values, you may get this value as 0.48. This is without filter, full wave rectifier, ripple factor. Similarly, you can find with filter ripple factor theoretically, that is 1 by 4 root 3 into F into C into RL. Here 2 root 3, here 4 root 3. All those are same. If you substitute all those values, you make it 0.02. Compared to this is less. So always for full wave rectifier, you'll get less ripple factor, 0.02. So here at the voltmeter, in the voltmeter, you can find VAC, VDC without filter and with filter. That should be equal to 0.48 without filter. If you connect a filter here, if you connect capacitive filter across load resistance, you may get 0.02. This is about rectifiers, both forward bias and both without filter and with filter. The next experiment is transistor CE characteristics or transistor characteristics in CE configuration. Transistor characteristics in CE configuration. The circuit is like this. So here we are using NPN transistor. NPN transistor. How to remember this circuit is, so this input junction should be forward bias, this output junction should be reverse bias. Otherwise, emitter base junction should be forward bias and collector emitter junction should be reverse bias. So here P is connecting to positive of the RPS. P is connecting to positive of the RPS. If it is positive, this one is negative. Or otherwise, N is connecting to negative. Positive is connecting to positive, N is connecting to negative. That is a forward bias. So here, for measuring voltage and currents, in parallel we are going to take on voltmeter, positive, negative. This is also positive, negative voltmeter. This is positive. That's why the adjacent ammeter is positive. Like this, you can remember the terminals. So NPN, emitter base junction forward bias, P is connecting to positive, N is connecting to negative. So these two should be parallel. This is positive, negative, this is positive, negative voltmeter. And this is positive, this adjacent terminal of the ammeter is positive. If it is positive, means this one is negative. At input side, we are taking one resistance for safety purpose. Similarly, come to output side. Here NPN, output should be reverse bias. N is connecting to positive. N is connecting to positive. If it is positive, means this one is negative. Negative. Reverse bias. Reverse bias. Here for this parallel, you can take one voltmeter. Voltmeter. This is positive. This is positive. This is negative. This is negative. Similarly, the adjacent ammeter is positive. This is positive. That is why adjacent ammeter is positive. This is negative. And for safety purpose, here we are using one resistance. Remember that input is forward bias, output is reverse bias. We are using NPN transistor. Don't forget to write the symbol and arrow is towards the emitter. So here we are having input voltage VBE, input current IB, output voltage VCE, output current IC. Then for input characteristics, here we have two types of characteristics. Input characteristics and output characteristics. For input characteristics, if you want to plot the input characteristics, output voltage should be constant. Here the output voltage is VCE. If you want to plot the input characteristics, output voltage should be constant. VCE should be constant on voltmeter. By varying the channel 2, this is channel 1, this is channel 2. By varying channel 2 RPS, keep VCE constant. Let us take 1 volt. 1 volt. By varying this, keep this on 1 volt. Then come to input side. Then vary the channel 1. Channel 1, 0. Keep this one 0. What is the voltage and current? Keep this one 0.1. What is the voltage and current? Keep this one 0.2. What is the voltage and current? So on. If you do like that, this is a P positive, N negative. Just like PN junction at forward bias, we will get the characteristics. This is about VC is equal to 1 characteristics. PN junction forward bias characteristics. PN junction forward bias characteristics. VC, VB and IB. Similarly, here we are repeating the same procedure for another constant value. By varying this, keep this VCE constant as 2 volts. 2 volts. By varying the second channel, second RPS, keep voltmeter value 2 volts. 2 volts. Then come to input side. Again, keep this one 0. What is the corresponding input voltage VB and input current IB. Then vary this into 0.1, 0.2, 0.3 and so on. Then note down the or tabulate the values for VB and IB. Then plot the graph between VB and IB for VC is equal to 2, we'll get like this. If VCE value is increases, the curve moves towards the right side. If VCE value is decreases, for example, VC is equal to 0, the curve moves towards the left side. Like this you'll get, any two values are enough. Then secondary, you can go for output characteristics. For input characteristics, output voltage should be constant. For output characteristics, input current should be constant. What is the input current? IB. IB. By varying this channel 1. Why? Because IB is in channel 1. By varying this RPS, keep this one as 0 microamps. 0 microamps. By varying this, keep this one 0 microamps. Then come to output side. Then by vary the second channel, channel 2, keep VC 0. What is the corresponding current? And by varying this RPS to 0, 0.1, 0.2, 0.3 and so on, note down this VC and IC values. Then look at the characteristics like this. VC and IC characteristics, output characteristics are like this. For IB is equal to 0. Similarly, you can go for IB, another constant value. Then come to input side, vary this channel 1, keep IB as constant. For example, 20 microamperes. 20 microamperes, vary this, keep this one 20 microamperes. Then come to output side, vary this RPS and note down the VC and IC values for the minimum 10 to 15 values. Then you'll get output characteristics like this. For IB is equal to 20 microamperes. From these characteristics, we have to find the current gain, voltage gain, input impedance and output admittance. If you know the formulas, then you can find these parameters. For example, beta is the current gain, output current by input current. If you know these curves, for example, from output characteristics, by taking any one IB, for this IB, what is the corresponding current? IC by IB will get beta value. Otherwise, delta IC by delta IB. IC2 minus IC1 by IB2 minus IB1. This is about transistor characteristics in CE configuration. Then come to next one, FET characteristics. This is the circuit. Here we are using N-channel JFET. N-channel JFET. That is why arrow is towards the inside the transistor. Arrow is inside or towards the source and drain. Then here we are using 100 kilo ohm resistance. Input side we are using an voltmeter, and here gate is connecting to, this is gate, drain and source. Gate is connecting to negative terminal and another one is positive. Gate is connecting to negative and positive. Here you can connect one voltmeter, and the output side you can connect one voltmeter, and output side you can take one ammeter. So here gate is connecting to negative and positive. Here voltmeter, you may take negative positive also, no problem. If you take positive negative in the voltmeter, you will get negative values. So here any manner you can take. Then come to output side, VDS is positive, drain is connecting to positive, source is connecting to negative. VDS is positive, VGS is negative. VGS is negative, VDS is positive. If it is positive means this adjacent diameter is positive. This adjacent diameter is positive, this is negative. These two are parallel, so this is positive, negative, positive, positive, negative, negative. Here also we have two types of characteristics. One is drain characteristics, second one is a transfer characteristics. For drain characteristics, keep VGS constant. VGS is constant. VGS is at a input side. By varying this channel 1, this is channel 1, this is channel 2. Otherwise RPS channel 1, RPS channel 2. By varying RPS channel 1, keep VGS constant. For example, let us take VGS is equal to -1. VS is equal to -1. Keep this one. Here you will get -1. By varying this, you will get -1 here. Then come to output side. Vary this VDS. Vary this VDS and find out the corresponding voltage and currents. Where this VDS, for example 0. What is the corresponding voltage and current? VDS is equal to 0.1 voltage and current, 0.2 voltage and current. Vary this into 0.3. What is the voltage and current? Like this, you can draw the characteristics for VDS versus ID. That is the drain characteristics. You will get characteristics like this. increases and slowly increases. This is a ohmic region and pinch off region you'll get. This is ohmic region and this is pinch off region. After that you may get saturation region. Saturation region, we are not operating up to saturation region. Up to here we are operating. If you operate up to saturation, the transistor may get damaged. So this is VGS is equal to -1. Similarly, you can repeat the same procedure for VGS is equal to -2. Then come to transfer characteristics. The transfer characteristics is between VGS and ID. For this purpose, you can take VDS constant. VDS, by varying this, keep VDS constant, then come to input side, vary the VGS 0.1, 0.2 like that. Like this, -0.5, 1, -1.5 and so on. Why? Because VGS is negative. If you find that at 0 you'll get maximum ID. If you increase negatively increasing the VGS, the current decreases slowly. VDS is equal to 0.5 and similarly VDS is equal to 1. You may draw the characteristics or you may tabulate the values for the transfer characteristics. This is about a FET characteristics. Similarly, you can go for CRO operation. Next experiment, CRO operation. Here, CRO is used for the measurement of voltage, current, time period as well as Lissajous patterns. So here I am finding first DC voltage measurement. For this purpose I am using one RPS. I am connecting one resistance. Here I am keeping RPS 5 volts. Fix this 5 volts. RPS positive is connecting to resistor one end and RPS negative is connected to resistor other end. Across this these two terminals on the breadboard you can connect. Across this you can connect CRO positive. We have a probe positive is connecting to resistor, probe negative is connecting to resistor other end. Then on the CRO you may display one straight line, that is from origin point to this is origin point to maximum. It will give some value. The distance between these two is nothing but amplitude into ohms per division knob. Channel 1 or channel 2 ohms per division knob. If you multiply those two, you may get DC voltage. For DC voltage purpose, I am connecting RPS here, keeping 5 volts, and I am displaying the straight line. DC that is straight line. On the CRO, you can find the distance or space between the origin point to the straight line. This is amplitude into ohms per division value. It may be channel 1 or channel 2. That may be 5 or 10 or 20, whatever it may be. You can multiply both, you will get 5 volts or approximately 5 volts. If there is any drop at 1 kilo ohm, you may get 4.8 to 4.9 like that. That is a DC voltage measurement. Similarly, you can go for AC voltage measurement. For that purpose, I am using function generator. From the function generator, I am giving sinusoidal signal. Press sinusoidal signal, then it will display sinusoidal signal. It may be at 1 kHz frequency, 1 kHz, 2 kHz, any frequency. At any frequency, you may give sine signal. Directly connecting positive of the CRO is connecting to the positive of the function generator, positive of the negative of the CRO is connecting to the negative of the function generator. Then sign will be displayed on the CRO. Then number of vertical divisions into ohms per division, you will get the voltage. Only vertical divisions is nothing but amplitude. Amplitude into ohms per division is nothing but voltage. Similarly, you can find the time period. Number of horizontal divisions into time for division. You will get time period. From the time period, you may get frequency. F is equal to 1 by T. You will get frequency. This frequency should be equal to this 1 kHz. Whatever we are applying, maximum same frequency will get from the time period. This is a AC voltage as well as time period measurement. Then come to Lissajous patterns. Take two function generators. One function generator keep 1 kHz. Second function generator can keep 2 kilohertz. Keep CRO in XY mode. the waveform will be display like this. Keep in dual mode. In channel 1 you can give sinusoidal signal as 1 kHz. Channel 2 you can give a sinusoidal signal as 2 kHz. Then keep in dual mode and in XY mode, then you'll get waveform like this. This is only Lissaj's pattern. Similarly, if these two values are different, this is 2 and this is 1, you'll get output like this, Lissaj's patterns. Similarly, you can vary for any frequency. If you are taking 1 kHz and 3 kHz, you may get like this. Horizontally 3 will get. Horizontally 3. This is 3, this is 1. Maybe you'll get like this. These are the Lissaj's patterns. Similarly, you can go for phase also. You may find phase also. This is about a CRO operation. Next one is UJT characteristics. UJT characteristics. This is the basic circuit for UJT characteristics. Here we can connect one voltmeter as well as ammeter, and output side you can take one voltmeter. This is VBB and this is VE and this is IE. For this UJT characteristics, keep VBB constant. By varying this, keep VBB constant. Then come to input side, vary this applied voltage VEE. Vary this applied voltage VEE and note down the VE and IE. This is a VE and IE. These two values you can note down. Keep 0. What is VE and what is IE? Keep this one 0.1. What is VE? What is IE? Otherwise 1, 2, 3, so on you can take. By varying this, you can find out these two values. You may get characteristics like this. For example, first value is VBB is equal to 5. You may get some negative values, and after that it is increases and decreases and again increases. Maybe you'll get some peak voltage, that is a VP. You'll get some valley voltage or low voltage, that is valley voltage. This is for VBB is equal to 5. After you will get increases. Peak voltage and valley voltage you will get. Those two you can find from the curve VBB is equal to 5. Similarly, you can do for another constant by varying this VBB. Keep this one 10 volts. Then come to input side, vary this VE and note down the VE and IE values. You may get the curve like this. For example, I am calculating for two constants. Then from this we have to find intrinsic standoff ratio, eta. Eta is equal to Vp minus Vd by Vbb. What is Vp value? Peak value. For example, for this one, Vp, whatever you will get, that is Vp, minus Vd is the diode cut-in voltage. For example, for this I got this is the peak voltage, Vp. This is a corresponding voltage, Vb, and this is a Vp. On y-axis we are taking voltage, on x-axis we are taking current. Remember this. This is the only change. On x-axis VE, on x-axis IE, y-axis VE. So here you may get Vp value, Vp substitute, and Vd, diode cut-in voltage 0.7 by Vbb. For example, for 5, you may get eta 1. Similarly, you can find for 10, that is eta 2 is equal to Vp some maximum peak value and value voltage. Maybe for Vbb is equal to 10, you will get peak voltage Vp and Vd is the 0.7 by Vbb is the 10. If we get substitute that, you will get eta 2. Then average of those two is nothing but eta. Eta is equal to eta 1 plus eta 2 by 2. This is the intrinsic standoff ratio. That is our aim, to find the intrinsic standoff ratio. Then go for amplifiers. So this is the CE amplifier circuit. Here we are connecting function generator, RPS, and output to the CRO. All we are using. Before that, from the function generator, directly we can connect to the CRO and give sinusoidal signal, and it may be 20 millivolts, input 20 millivolts at 1 kHz frequency. At 1 kHz frequency, keep input as 20 millivolts. First, you can connect directly from the function generator to the CRO, positive to positive, negative to negative. Press sign signal and keep this one as 20 millivolts, adjust into 20 millivolts, or it may be 50 millivolts, or it may be 100 millivolts. Then connect the circuit as per circuit diagram. Function generator to the this resistance, and RPS to positive here, negative ground, CRO positive here, negative ground. Then connect circuit as per this, and by varying this frequency, 100 hertz, keep 100 hertz, what is the output voltage? 200 hertz, what is the output voltage? Like this. For varying this frequency, note down the output voltage. Then gain is V0 by Vi. For example, for 100, I will get 50 volts, 50 millivolts, 50 by 20. That is the gain, 50 by 20. For all, input is same, 50 by 20. Then 20 log 50 by 20 is gain in dB. You can find all the values. You can take some set of values, then plot the graph between frequency and gain in dB. Here in CE, we may get the curve increases up to some point, then you may get some constant portion and decreases. Where we'll get the maximum gain? For example, this is the maximum gain 10 dB. From that, you can take 3 dB line. 10 minus 3, you make it 7. This is 7 dB. At 7 dB, we can draw one line. From 10, subtract 3. At a 3 dB line, you will get the efficient bandwidth. That is at 7, you can draw one graph, one line. This line will touch the curve on 2 points, that is F2 and F1. If you take F2 minus F1, that is the bandwidth. For any amplifier, you can find the bandwidth. That should be high. That is the best amplifier. This is CE amplifier. If you want to find emitter follower or CC amplifier, you can take output across emitter. Same circuit, you can get the output across the emitter, not at the collector. And for CC or emitter follower, both input and outputs are same. Input is, for example, 20 millivolts. Output also you may get 20 millivolts like that. Then gain is equal to 1, 20 by 20, 1. So gain in dB is 0. 20 log 1 is 0. Then the frequency response curve is like this, straight line. Bandwidth is infinity. Similarly, you can go for some other amplifiers. It may be common base amplifier or FET amplifier, anything. So these are the amplifiers. Thank you.